Welcome to your deep dive all about sedimentary rocks. I'm ready to get into it.
Me too.
It's just amazing to me like how a rock can tell us so much about like the history of our planet.
Yeah.
So you sent in some slides titled Sedimentary Rocks 101, which tells me you're ready for this.
Yeah.
We're going to be looking into the different types of sedimentary rocks, how they form, and even where you might find them.
Sounds good. What's fascinating is they're not just like static objects. They're part of a cycle. They're constantly changing and reforming over millions of years.
Okay, so let's start with this rock cycle thing.
Yeah.
Slide 2 has like a cool diagram that shows how it all works.
It all begins with igneous rocks, formed from cooled and hardened magma, like think of a volcano erupting.
Okay.
Over time, these igneous rocks are broken down into smaller pieces called sediment through weathering and erosion.
So like those majestic mountains slowly crumbling into tiny grains of sand.
Exactly. Wind, water, or even ice can transport this sediment over vast distances. Imagine a powerful river carrying sand and silt downstream, or a glacier carving its way through a mountain range.
Wow.
Eventually, this sediment is deposited, often in layers, at the bottom of lakes, oceans, or even deserts.
So it's like nature's way of like sorting and layering these tiny rock fragments?
Yes. As more and more layers pile up, the weight compacts the sediment, squeezing out water and air. Dissolved minerals in the water seep through the gaps, crystallizing, acting like a glue to cement the particles together.
And voila, we have a sedimentary rock. It's like Mother Nature's own construction project, building these rocks layer by layer over millions of years.
Precisely. But the journey doesn't end there. If our sedimentary rock gets buried deep enough and exposed to intense heat and pressure, it can transform into a metamorphic rock. And if it melts completely, it becomes magma, ready to start the cycle all over again.
Whoa. It's this incredible ongoing transformation. Okay, so let's zoom in on that step, where the sediment turns into rock. Slide 3 shows like some stunning layers. It looks like a colorful layer cake.
Those layers, called strata, are like pages in Earth's history book. Each layer represents a different period of deposition, capturing information about the environment at that time.
Oh, so like if we look at those layers closely, we can learn about what the Earth's was like millions of years ago.
Exactly. Imagine a layer of sandstone with fine, well-sorted grains. That tells us the sediment was likely deposited in a calm environment, like a shallow sea or a lake. But if we see a layer with a jumble of different sized particles, from sand to pebbles to boulders, that suggests a more energetic environment, perhaps a raging river or a glacier.
So it's like becoming a detective, using these clues to piece together the history of the Earth.
Precisely. And remember, those underwater avalanches we talked about, the turbidity currents, they leave behind a unique pattern in the rock called graded bedding, where the largest particles are at the bottom and gradually get finer towards the top.
Wait, so you're telling me we can actually see evidence of these underwater avalanches in the rocks?
Yeah.
That's incredible.
It is. And it's just one example of how sedimentary rocks can capture these dynamic events from the past.
Okay, I'm ready to dive into how these sedimentary rocks are formed. Slide 4 says they're not just made from broken down rocks.
That's right. Sedimentary rocks are incredibly diverse. They can be formed from deposits of pre-existing rocks and minerals, but also from the remains of once living organisms.
Really?
That's why we have three main classifications of sedimentary rocks: clastic, chemical, and organic.
Ooh, 3 different categories? Okay, I'm ready to break this down.
Clastic rocks are the puzzle piece rocks,
Yeah.
formed from fragments or clasts of other rocks that have been weathered and eroded.
So like a jigsaw puzzle of rock bits and pieces all cemented together.
Exactly. And just like puzzle pieces come in different sizes, so do these rock fragments. The size of the fragments is actually how we classify clastic sedimentary rocks.
So a rock made from large, chunky pieces would be different from one made from fine, powdery stuff.
Precisely. Imagine you're holding a rock made of large, rounded pebbles, all cemented together. That's a conglomerate, a rock that's traveled a long way, perhaps carried by an ancient river.
So it's like holding a piece of a prehistoric riverbed in my hand. What about rocks made from smaller pieces?
If you come across a rock that feels gritty, like sandpaper, you're probably looking at sandstone, which is made from sand-sized grains. It's a very common rock, often found in deserts, beaches, and ancient riverbeds.
Sandstone. It's like holding a fossilized beach in your hand.
Indeed. And if we go even smaller, we get to rocks like siltstone and shale, made from even finer particles, like silt and clay. These rocks often form in calm, quiet environments, like the bottom of lakes or the deep ocean.
So from giant boulders to microscopic clay particles, it's amazing how the size of the fragments creates such a variety of rocks.
It is. And each of these clastic rocks tells a story about the environment where it formed. The size, shape, and sorting of the clasts, along with the type of cementing material, all provide valuable clues to geologists.
Okay, I think I've got a handle on clastic rocks. What about those chemical sedimentary rocks? The ones formed from dissolved minerals.
Ah, yes. Chemical sedimentary rocks are like the alchemists of the rock world, formed through precipitation rather than mechanical breakdown.
And we talked about rock salt earlier, right? That's the kind we sprinkle on our food.
Exactly. Rock salt, or halite, forms when salt water evaporates, leaving behind the dissolved salt crystals. Imagine vast, prehistoric salt flats, stretching as far as the eye can see, all formed through this process of evaporation.
That's an incredible image. What other treasures are hidden in this category of chemical sedimentary rocks?
Well, limestone is a big one. It's composed primarily of calcium carbonate, often derived from the shells and skeletons of marine organisms.
So, like, the remains of ancient sea creatures are now part of our homes and farms. That's an amazing connection. What else?
We also have dolostone, similar to limestone but containing magnesium. Then there's chert, a hard, fine-grained rock made of silica. Chert was highly prized by early humans for making tools and weapons because it can be chipped into very sharp edges.
It's fascinating to think about our ancestors using these rocks to create tools and survive.
Yeah.
Okay, so we've got salt, limestone, dolostone, chert. Any other examples of these chemical wonders?
One more that might surprise you, iron ore. Some types of iron ore are actually chemical sedimentary rocks formed when iron-rich minerals precipitate out of solution. These deposits have been crucial for the development of human civilization, providing the raw material for tools, weapons, and infrastructure.
Wow, I never realized how much we rely on these chemical sedimentary rocks. Okay, on to the last category, those fascinating organic sedimentary rocks. Slide 8 shows a picture of, is that a pile of coal?
It is, and coal is a prime example of an organic sedimentary rock. These rocks form from the accumulation and deposition of dead plants and animals. Can you believe it? Rocks made from the building blocks of life itself.
So is coal basically fossilized plants?
In essence, yes. It forms in swampy environments where dead plant matter accumulates in layers. Over millions of years, this plant matter gets buried, compacted, and transformed by heat and pressure, eventually turning into coal.
So like those lush prehistoric swamps became the energy source that powers our world today. That's mind-blowing.
It really is. And speaking of fossils, we can often find those incredible remnants of ancient life in organic sedimentary rocks. Slide 10 dives into the world of fossils and how they form.
Wait, so those fossils are like snapshots of what life was like millions of years ago preserved in these rocks. This is getting really interesting.
It is, and we'll be diving into all the details of fossil formation in the next part of our deep dive.
I can't wait. But for now, I think we need a little break to process all this amazing information about the different types of sedimentary rocks. We've covered a lot of ground already, from those gritty sandstones to those ancient salt flats.
We have. And in the next part, we'll explore even more fascinating details, including how to identify these rocks in the real world and the surprising ways we use them in our everyday lives.
Sounds good. I'm ready to learn even more about these geological wonders.
Great. Welcome back to our deep dive into sedimentary rocks. It's incredible how much information these rocks hold about our planet's past.
I know, right? We've already uncovered so much from the rock cycle to those ancient salt flats, and we even touched on fossils.
And believe it or not, we've only just scratched the surface. There's a whole world of detail within each category of sedimentary rock.
Well, I'm ready to dig deeper. Slide 5 shows a close-up of a rock, and it looks like the grains are getting smaller as you go up. The caption says it's called graded bedding. What's the story behind this pattern?
Graded bedding. It's a fascinating feature that tells us a lot about how the sediment was deposited. Remember those turbidity currents we talked about, those underwater avalanches?
Yeah, those sounded pretty intense.
They are. Graded bedding is often a result of those events. Imagine a sudden rush of sediment and water cascading down a slope like an underwater landslide. As the current loses energy, the largest, heaviest particles settle out first.
So the boulders and cobbles would be at the bottom?
Exactly. Then, as the current slows further, the smaller particles like sand and silt start to settle on top. And finally, the finest particles like clay settle out last, forming the topmost layer.
It's like nature's own sorting mechanism, creating these layers based on the size of the particles. So when I see graded bedding in a rock, we know there was some serious underwater action involved.
Precisely. It's a powerful clue that helps geologists reconstruct ancient environments and understand the forces that shaped our planet.
Okay, let's get back to those different types of sedimentary rocks. We talked about clastic rocks being like puzzle pieces. What other stories can those rocks tell us?
Clastic sedimentary rocks are incredibly diverse. But remember, they're all formed from fragments of other rocks. And those fragments, the clasts, come in all shapes and sizes.
Right. We talked about conglomerate with its large rounded pebbles. What about a rock with angular fragments, those that haven't traveled as far?
You're thinking of breccia. Breccia is also made from large clasts. But these fragments are angular, not rounded. This suggests they didn't travel far from their source before being cemented together. You often find breccia near fault zones or areas where landslides have occurred.
Interesting. So conglomerate is for well-traveled clasts, and breccia is for the stay-at-home types. What about those smaller grains like sand?
Sandstone, of course. As the name suggests, it's made from sand-sized particles, mostly quartz. It's a common rock often found in deserts, beaches, and ancient riverbeds.
So if I find a piece of sandstone, I could be holding a piece of an ancient beach or desert?
Exactly. And if we go even smaller, we get to siltstone and shale, made from even finer particles like silt and clay. These rocks often form in calm, quiet environments, like deep lakes or the ocean floor.
From giant boulders to microscopic clay particles, it's amazing how the size of the fragments creates such a variety of rocks.
It is. And remember, each of these clastic rocks tells a story about the environment where it formed.
Okay, I'm ready to move on to those chemical sedimentary rocks, the ones formed from dissolved minerals. We talked about rock salt forming from evaporated salt water. What other examples are out there?
Let's talk about limestone. It's a major player in the world of sedimentary rocks and is composed primarily of calcium carbonate, often derived from the shells and skeletons of marine organisms.
Wait, so limestone is basically made from ancient sea creatures?
Essentially, yes.
Oh.
Imagine a warm, shallow sea teeming with life. As these organisms die, their shells and skeletons accumulate on the seafloor. Over time, these remains get buried, compacted, and cemented together to form limestone.
So those ancient seas are now preserved in these rocks. That's incredible.
It is. Limestone is a versatile rock used in everything from building materials to agricultural lime. You might even have some in your own home.
Wow, I never thought about it that way. What other chemical sedimentary rocks should we know about?
We also have dolostone, which is similar to limestone but contains magnesium. Then there's chert, a hard, fine-grained rock made of silica. Chert was highly prized by early humans for making tools and weapons because it can be chipped into very sharp edges.
It's amazing how these rocks formed through chemical processes have played such an important role in human history.
They have. And let's not forget about iron ore. Some types of iron ore are actually chemical sedimentary rocks formed when iron-rich minerals precipitate out of solution. These deposits have been crucial for the development of human civilization.
Okay, on to the last category, those fascinating organic sedimentary rocks. We talked about coal being fossilized plants. What other examples are there besides fossilized plants?
Well, there's oil shale, a fine-grained rock that contains a significant amount of organic matter called kerogen. When heated, this kerogen can be converted into oil and gas, making oil shale a potential energy source for the future.
So it's like a rock that's halfway to becoming oil. What else is there?
Another interesting example is coquina, a rock composed almost entirely of shell fragments. It's a porous rock often found in coastal areas where wave action breaks down shells and deposits them in layers. You mentioned you loved going to the beach. You might have even walked on coquina without realizing it.
Really? So it's like a shell graveyard turned to stone. I'm going to have to look out for that next time I'm at the beach.
Exactly. And just like with other sedimentary rocks, coquina can tell us a lot about the environment where it formed.
This is all so fascinating. Okay, let's dive deeper into coal formation. Slide 9 had some pretty cool images of swampy areas.
Coal formation is a fascinating process that takes place over millions of years. It all starts in swampy environments where dead plant matter accumulates in layers.
Like those ancient forests we saw in the images.
Exactly. These swampy areas are often low in oxygen, which slows down the decomposition of plant matter. As more and more layers of dead plants build up, they get compacted by the weight of the overlying sediment.
It's like a giant prehistoric compost pile. What happens next?
As the layers get buried deeper, the temperature and pressure increase, causing chemical and physical changes in the plant matter. This process, called coalification, transforms the plant material into peat, the first stage in coal formation.
Peat, like the stuff they use in gardens.
That's right. Peat is soft and spongy with a high water content. But as the peat gets buried even deeper and exposed to more heat and pressure, it continues to transform. The water content decreases and the carbon content increases, eventually turning the peat into lignite, a low-grade type of coal.
So it's like the peat is getting squeezed and cooked into something more solid.
Exactly. And the transformation doesn't stop there. With continued heat and pressure, lignite can be transformed into subbituminous coal, then bituminous coal, and finally anthracite, the hardest and most carbon-rich type of coal.
So from soggy peat to shiny anthracite, it's amazing how heat and pressure can completely transform something over millions of years.
It is. And each stage in coal formation represents a different level of energy concentration. Anthracite, with its high carbon content, burns much hotter and cleaner than lignite, making it a more desirable fuel source.
It's fascinating how this whole process captures energy from ancient sunlight, storing it in these rocks for us to use today.
Indeed. Coal formation is a testament to the incredible power of geological processes and the interconnectedness of Earth systems.
Okay, I'm ready for another deep dive. You mentioned fossils earlier. What about fossil formation? Slide 10 showed some amazing examples.
Fossil formation is truly remarkable. It's a delicate dance between preservation and destruction, where the remains of ancient life are transformed into lasting records.
And we talked about how fossils are often found in sedimentary rocks, right?
Exactly. Sedimentary rocks are ideal for fossil preservation because they form through the gradual accumulation of sediment, which can gently bury and protect the remains of organisms.
So the same processes that create these rocks also help preserve these glimpses into the past.
Precisely. Now, most fossils form when organisms are quickly buried by sediment. This protects them from scavengers and the elements, giving them a chance to be preserved.
So it's like winning the lottery for a creature to become a fossil.
In a way, yes. It's a rare event, but when it happens, the results can be spectacular. Now, the soft tissues of an organism usually decay quickly after death. What's left behind are the hard parts: bones, teeth, shells, and sometimes even woody tissues from plants.
And then those hard parts get replaced by minerals,
Right.
turning them to stone.
Exactly. Over time, minerals dissolved in groundwater seep into the remaining hard parts, slowly replacing the original organic material in a process called petrification.
So it's like a slow motion mineral swap, preserving the shape of the original organism in stone. Incredible. What about those trace fossils, the footprints and burrows we talked about earlier?
Trace fossils are fascinating because they capture the activity of ancient organisms rather than their physical remains. These traces are often preserved as impressions or casts in sedimentary rocks.
So like a dinosaur stepping in mud, leaving a footprint that eventually hardens into rock.
Exactly. Or imagine a worm burrowing through sand, creating a tunnel that gets filled with sediment and eventually becomes fossilized.
It's like becoming detectives, piecing together clues from these rocks to understand how ancient creatures lived and moved.
Indeed. Trace fossils give us valuable insights into the behavior, locomotion, and even the social interactions of extinct organisms.
This is all so amazing. I can't wait to get out there and start looking for fossils. But before I do, Slide 11 had some tips on identifying sedimentary rocks in the real world, and it looks like there's a lot to pay attention to.
You're right. Identifying sedimentary rocks is like solving a puzzle, piecing together clues to unravel their story. And the first clue is always observation.
So what should we be looking for?
Start with the basics. Grain size, shape, and sorting. Are the grains visible to the naked eye, or do you need a magnifying glass? Are they rounded, angular, or a mix of both? Are they all roughly the same size, or is there a jumble of different sizes? These observations can tell you a lot about the rock's origin and history.
Okay, so I'm looking at a rock right now, and the grains are pretty small. I can barely see them. It also has these distinct layers, and it feels kind of smooth. What could it be?
Those are excellent observations. Based on what you've described, you might be holding a sample of shale. Remember, shale is made from tiny clay particles, which gives it that smooth texture. And those distinct layers are a classic feature of sedimentary rocks called bedding.
Whoa, so I'm holding a piece of ancient mud. What else should I be looking for?
Don't forget about composition. What are the grains made of? Are they mostly quartz feldspar or maybe even fragments of shells? This can tell you about the source of the sediment and the environment where the rock formed.
So like a geological fingerprint. What about the cement holding the grains together?
The cementing material is another important clue. Is it calcite silica or iron oxide? The type of cement can affect the rock's color hardness and even its resistance to weathering and erosion.
It's like a whole world of detail hidden within these rocks. The slide also mentions looking for sedimentary structures. What are those?
Sedimentary structures are features that form during or shortly after sediment deposition. They can provide valuable clues about the environment where the rock formed.
Can you give me some examples?
Of course. We've already talked about bedding, but there's also cross-bedding, which forms when sediment is deposited at an angle like in sand dunes or river channels. Ripple marks, those wavy patterns we see on beaches, can also be preserved in rock, telling us about ancient water currents. Mud cracks formed when mud dries and shrinks can indicate periods of exposure to air.
So it's like reading a history book written in stone.
Exactly. Each of these structures provides a glimpse into the past, helping us reconstruct ancient environments and understand the processes that shaped our planet.
This is so cool. The slide even mentions using a hand lens or microscope for a closer look.
Absolutely. A closer examination can reveal amazing details you might otherwise miss. You might discover tiny fossils, intricate mineral patterns, or subtle variations in grain size and shape.
It's like becoming a rock detective armed with a magnifying glass and curiosity. I'm definitely going to be looking at rocks in a whole new way from now on.
That's the spirit. Sedimentary rocks are all around us waiting to tell their stories. And with a little knowledge and observation, you can unlock their secrets and connect with the vast history of our planet.
Well, I'm feeling inspired to go on a rock hunting adventure. But before I do, I think we need to delve into how we actually use these amazing rocks. Slide 12 had some pretty surprising
You're
examples.
right. Sedimentary rocks are not just geological curiosities. They play a vital role in our everyday lives. They're essential for construction, energy production, agriculture, and even art and decoration.
So how do we use them in construction?
While limestone and sandstone, both sedimentary rocks, have been used as building materials for centuries. Think of ancient pyramids, grand cathedrals, and even modern skyscrapers, all made possible by the strength and durability of these rocks.
So these rocks literally shape our world. What about energy production?
Coal, as we discussed earlier, is a major source of electricity worldwide. It's a sedimentary rock formed from the remains of ancient plants. And don't forget oil and natural gas, which are also found in sedimentary rock layers. These fossil fuels power our homes, our cars, and our industries.
It's amazing how these ancient rocks are still so vital to our modern world. What about agriculture? How do sedimentary rocks play a role there?
Sedimentary rocks are essential for soil health and fertility. Limestone, for example, is often used as a soil amendment to neutralize acidic soils. It helps to create the optimal pH balance for plant growth. And phosphate rock, another sedimentary rock, is a key ingredient in fertilizers, providing essential nutrients for crops.
So from building our homes to growing our food, sedimentary rocks are essential for our survival. What about art and decoration? How do they fit in there?
Sedimentary rocks can be surprisingly beautiful. Gemstones like opals and turquoise, often found in sedimentary rock formations, are prized for their vibrant colors and unique patterns. And marble, a metamorphic rock derived from limestone, is renowned for its elegance and durability, used for everything from sculptures to countertops.
It's like these rocks are woven into every aspect of our lives.
They truly are. Sedimentary rocks are not just about the past, they're very much a part of our present and future. They provide the raw materials for our homes, the energy that powers our lives, and the inspiration for our art and creativity.
Well, I don't know about you, but I'm feeling a newfound appreciation for every rock I see now. This has been an incredible journey. But before we wrap up this deep dive, I think we need to take a closer look at the rock cycle itself. It's the foundation for everything we've talked about, and slide 2 has a great diagram that lays it all out.
You're right. The rock cycle is the grand unifying concept in geology, connecting all three major rock types: igneous, sedimentary, and metamorphic. It's a continuous process of creation, destruction, and transformation driven by the Earth's internal heat and the forces of weathering and erosion.
Okay, so let's break it down. The diagram shows that the cycle starts with igneous rocks. What are they and how do they form?
Igneous rocks are the fire-borne rocks formed from the cooling and crystallization of magma, which is molten rock found beneath the Earth's surface.
So when volcanoes erupt and lava flows, it eventually cools and hardens into igneous rock.
Exactly. That's one way igneous rocks form, called extrusive igneous rocks. They cool quickly at the surface, often forming fine-grained textures. But igneous rocks can also form deep underground when magma slowly cools and crystallizes within the Earth's crust. These are called intrusive igneous rocks, and they tend to have coarser grained textures because the crystals have more time to grow.
So granite, that beautiful rock with large crystals, is an intrusive igneous rock.
You got it. Granite is a classic example of an intrusive igneous rock. It forms deep underground, slowly cooling over millions of years, allowing those large crystals to develop.
Okay, so we've got our igneous rocks. What happens next in the cycle?
The next step is weathering and erosion. Weathering is the breakdown of rocks at the Earth's surface, caused by factors like temperature changes, wind, rain, and even the actions of plants and animals. Erosion, on the other hand, is the transport of weathered rock fragments away from their source, usually by wind, water, or ice.
So weathering is like breaking the rocks down, and erosion is like carrying the pieces away.
Precisely. And those broken down rock fragments, what we call sediment, are the building blocks of sedimentary rocks.
Okay, so the sediment gets transported and eventually deposited somewhere. What happens then?
Over time, layers of sediment accumulate in various environments like riverbeds, lakes, oceans, and even deserts. As more and more layers pile up, the weight of the overlying sediment compacts the lower layers.
So it's like squeezing the water out of a sponge.
In a way, yes. The compaction process forces out water and air, bringing the sediment grains closer together.
And then those grains get cemented together to form solid rock.
Exactly. Dissolved minerals in groundwater seep through the spaces between the sediment grains. As the water evaporates, these minerals crystallize, forming a natural cement that binds the grains together.
So it's like gluing the pieces of the puzzle together.
Indeed. And that's how sedimentary rocks are born. They're formed from the accumulated and cemented fragments of pre-existing rocks, minerals, and sometimes even the remains of organisms.
It's amazing how this whole process transforms loose sediment into solid rock layer by layer over millions of years.
It is. And the story doesn't end there. The rock cycle is a continuous loop, and sedimentary rocks can be transformed further.
What happens to them?
If a sedimentary rock is buried deep enough within the Earth's crust, it can be exposed to intense heat and pressure. These conditions can transform the rock, altering its mineral composition and texture, creating a metamorphic rock.
So it's like baking a cake. The heat and pressure transform the ingredients into something new.
That's a great analogy. Metamorphic rocks are essentially changed form rocks. They retain some of their original characteristics, but they've been altered by the intense conditions deep within the Earth.
Can you give me some examples of metamorphic rocks?
Of course. Marble, which we mentioned earlier, is a metamorphic rock formed from limestone. Slate, a fine-grained rock often used for roofing and flooring, is a metamorphic rock derived from shale. And gneiss, a rock with distinctive bands of minerals, can be formed from a variety of parent rocks, including granite and sandstone.
So even those tough igneous and sedimentary rocks can be transformed into something new. What happens if the metamorphic rock gets buried even deeper?
If the temperature and pressure become extreme enough, the metamorphic rock can actually melt, turning back into magma. This completes the rock cycle, bringing us back to the beginning.
Wow, it's this incredible ongoing transformation. Igneous rocks to sedimentary rocks to metamorphic rocks and back to magma. It's mind-blowing.
It is. The rock cycle is a testament to the dynamic nature of our planet, a constant interplay of forces that shape and reshape the Earth's surface over millions of years.
I'm starting to see why geologists are so fascinated by this cycle. It's not just about rocks, it's about understanding the history of our planet and the forces that continue to shape it today.
Exactly. The rock cycle is a fundamental concept in geology, providing a framework for understanding how rocks form, change, and interact over time. And remember, you provided those Sedimentary Rocks 101 slides because you were interested in learning more about these fascinating rocks.
Right. We've talked about how they form their different types and even how to identify them, but I'm also curious about where we can actually find these rocks. Is it just a matter of looking down?
Well, that's a great question, and it leads us perfectly into the final part of our deep dive. We'll be exploring where to find sedimentary rocks, the stories they can tell us about past climates, and even how they connect to the rock cycle.
This is so exciting. I'm ready to see where this journey takes us. Welcome back to our final part of this deep dive into sedimentary rocks.
Yeah.
I'm feeling pretty confident in my sedimentary rock knowledge at this point.
Good.
We've gone through the rock cycle. We talked about the three main categories: clastic, chemical, and organic.
Yeah.
We even dove into how to identify those rocks, like real geologists.
You're getting it.
I'm remembering that you sent in those Sedimentary Rocks 101 slides, which makes me think you're probably, really curious about where these rocks were actually found.
Right.
We've talked about how they form, but, where are they?
Well, sedimentary rocks are actually incredibly widespread. I mean, they cover something like 75% of the Earth's surface.
Mm-hmm.
But finding them isn't always as simple as, looking down.
Right.
Sometimes they're hidden beneath layers of soil, vegetation, or even, younger rocks.
Oh, okay.
But with a little knowledge and observation, you can become a, sedimentary rock detective.
Okay, I'm ready to put on my detective hat. Where should we start our search?
One of the best places to find sedimentary rocks is in areas with exposed bedrock.
Okay.
Think of canyons, cliffs, mountainsides, even road cuts. Places where, like, layers of rock have been revealed.
So like those colorful layers you see in pictures of national parks, those are sedimentary rocks.
Yeah, exactly.
Yeah.
The Grand Canyon, for instance.
Oh, yeah.
It's like a world-renowned showcase of sedimentary rocks,
Mm.
layer upon layer of sandstone, limestone, shale exposed over millions of years of erosion. Imagine standing at the rim of that canyon, looking out over those vast layers of rock, each telling a story about Earth's ancient past. It's really humbling.
Wow, it's like a giant history book carved into the earth. What about like less dramatic landscapes?
Even then, you can often find clues to the presence of sedimentary rocks.
Hmm.
Look for areas with rounded hills, gentle slopes, stream beds where water has, like, carved through the rock.
So if I'm out hiking and I see a stream cutting through a rocky area, there's a good chance I'm looking at sedimentary rocks.
Exactly. Rivers and streams, they're powerful erosive forces. They often carve through sedimentary rock layers and expose them for us to see. Pay attention to the shapes and patterns of the rocks. Do you see layering or bedding? Are the rocks made up of fragments or crystals? These are all clues that can help you identify sedimentary rocks.
Okay, so canyons, cliffs, stream beds, those all make sense. What about beaches?
Yeah.
Aren't those covered in sand, which is like a key ingredient in sedimentary rocks?
Absolutely. Beaches are fantastic places to observe sedimentary processes in action. The sand that you see is essentially sediment in transit, constantly being moved and sorted by the waves and currents. Think of those waves crashing on the shore, breaking down shells, rocks into smaller and smaller pieces.
So like those beautiful sandy beaches are giant sedimentary rock factories, just like in the making.
Indeed. Over time, if conditions are right, that sand can be buried, compacted, and cemented together to form sandstone.
Wow. It's amazing how something as familiar as a beach can hold so much geological significance. What about those, like, vast deserts we see in photos? Are there sedimentary rocks hiding there too?
Deserts are actually prime locations for finding sedimentary rocks.
Really?
Think about it. Deserts, they're dry environments, little vegetation to cover the rocks,
Hmm.
makes them easier to spot.
Oh, okay.
And wind, such a powerful erosive force in deserts, often sculpts the rocks into fascinating shapes and exposes layers of sedimentary rock.
So those iconic rock formations we see in desert landscapes are actually sculpted sedimentary rocks.
Exactly. Arches National Park, for example, in Utah.
Yeah.
It's famous for its stunning sandstone arches carved by wind and water over millions of years.
It's just incredible how these seemingly like barren landscapes can hold such geological treasures.
Oh no.
Okay, so we've covered canyons, cliffs, stream beds, beaches, and deserts. Anywhere else we should be on the lookout for sedimentary rocks?
Well, don't forget about caves.
Oh, yeah.
Many caves are formed within limestone, which is a soluble rock that can be dissolved by slightly acidic water. Over time, this dissolution process creates those underground chambers, passages, even like spectacular formations like stalactites and stalagmites.
So, like, exploring a cave is like taking a journey through the heart of a sedimentary rock.
Indeed. And the formations you see inside a cave, those intricate patterns of minerals, those are all testaments to those slow and steady processes of deposition and dissolution that shape sedimentary rocks.
This is so cool. Okay, before we wrap up our last part of our deep dive, I want to go back to something we touched on earlier about how sedimentary rocks can, like, give us clues about past climates. How is that possible?
That's a great question. Sedimentary rocks are like ancient weather reports. They record the environmental conditions that existed when they formed. By studying the types of minerals present, the size and shape of sediment grains, and even the types of fossils preserved, we can actually, like, piece together a picture of past climates.
So it's like being a paleoclimatologist, using the rocks as our time machine. Can you give me some examples of how sedimentary rocks reveal those climate clues?
Sure. For instance, coal deposits.
Yeah.
As we've discussed, they form in swampy environments.
Hmm.
So finding expensive coal beds suggests that the climate in that region was once warm and humid, supporting, lush vegetation.
So a lump of coal is like a reminder of a prehistoric tropical paradise.
Kind of.
What other clues can we find?
Well, glacial deposits, like those found in areas that were once covered by ice sheets, tell a different story. These deposits often contain a jumble of different sized sediment grains from clay to boulders, indicating that the sediment was transported and deposited by glaciers, which are powerful erosive forces that can move a wide range of particle sizes.
So finding those like jumbled up deposits, that's like a sign that the climate was once much colder.
Exactly. And we can even find clues about ancient sea levels in sedimentary rocks.
Oh, wow.
For example, finding marine fossils in rocks that are now far inland suggests that sea levels were once much higher, flooding areas that are now dry land.
It's incredible how these rocks can tell us so much about like the history of our planet. It's like they're whispering secrets from the past.
Indeed. Sedimentary rocks are a testament to the power of those geological processes and the interconnectedness of Earth's systems.
Yeah.
By studying them carefully, we can gain a deeper understanding of our planet's history, its changing climate, and, the evolution of life itself.
Well, I think we've officially reached the end of our sedimentary rock journey.
We have.
We've explored their formation, the types, their identification. We talked about how we use them, and even how they can help us understand past climates.
We covered a lot. It's been a fascinating deep dive.
It really has. And to our listener, thanks for joining us on this incredible journey into the world of sedimentary rocks. And remember, those rocks that you see every day, they might just be ancient time capsules waiting to share their stories.
Happy rock hunting.